Hello, statistics people out there. We're going to play around with probability right now. So I'm going to switch to my desktop and we'll go over a few problems. Okay, so we're going to look at mutually exclusive events, and the next recording I'll go over independent events. They're two different ideas, they're both important. So let's say we're playing with rolling a six-sided die, and let's just roll one at a time for now. We can do two later. So I might want to look at finding the probability of an even number. And so to figure out that out, I have to list all possible even events. So sample space is getting a 1, 2, 3, 4, 5, 6, whatever. So let's write that down. My sample space here are all possible outcomes. And that's equal to the set 1, 2, 3, 4, 5, 6. I also have another event called even number within that sample space. And even, I believe, is getting a 2, a 4, or a 6. And so probability here would be theoretical. There are 3 different possibilities for an even number. I believe they're each equally likely. And then there are 6 equally likely events total. So the probability here is 3/6. You could reduce that to 1/2 or 50% if you wish. 3/6 is a fine answer also. So we have a lot of ways we can write that answer. What I want to take a look at here is looking at the probability of getting an even number or a number that is less than 5. So let's look at the set less than 5. So a number is less than 5. That would be 1 or 2 or 3 or 4. So then I need to look at, well, which numbers are even or less than 5? And so I could start making a list of those options here. So if I, underneath here, let's write down which numbers are that. So I've got the even numbers, 2, 4, and 6. Numbers that are less than 5 would be 1. Now I'm not going to write 2 because I already wrote it down, but 3. And I'm not going to write 4 because I already wrote it down. Okay. So there are 1, 2, 3, 4, 5 numbers that are either even or less than 5. So I believe the probability here is 5 out of 6. So in order to find a probability, we have to understand our sample space, and we have to understand what particular set or sets we need to combine or look at. One might look at that and say, or, I just combine them. So a lot of times with ors, we add them. So is that the same of probability of being an even number plus the probability of being less than 5? And you're probably already seeing the problem with that. An even number is 3 out of 6. A number less than 5 is 4 out of 6. And if I try to combine those, I get 7 out of 6, which is impossible because it's greater than 1. Probabilities cannot be greater than 1. They can be 1 at most, so something's wrong here. And the problem is we double counted some numbers here. We double counted the 2 and the 4 in both of these. I can only count them once. So to adjust for that, what we do is we subtract from this what they have in common. So that would be being even and less than 5. Okay, so altogether, I could take my 3/6 probability of being even plus the probability of being less than 5, 4/6, but now I have to subtract the numbers that are both even and less than 5, and that would be the 2 and the 4. So that would be 2/6. So 3 and 4 is 7 minus 2 gives me 5, 6, which matches the other way that I did it. So the idea of mutually exclusive means that 2 events don't have anything in common, but these events did. So let's summarize that. Mutually exclusive. So mutual, common, exclusive, they exclude nothing. So nothing can be in common. So that means nothing in common. So common are the things they have together, like this and that. So for two events, the probability of A and B, that means what they have in common. That has to be nothing if they're mutually exclusive. Okay, so mutually exclusive means nothing in common, which means the probability of A and B happens to be 0, which makes ORs easier to deal with. Because the rule for ORs in general is the probability of having A or B is equal to the probability of A plus the probability of B minus their intersection. And if I know their intersection is empty, then I can ignore that and just do the addition. So that's the general rule. If it's mutually exclusive, then the rule simplifies a little. And I get the probability of A or B is simply the probability of A plus the probability of B. But we can't always assume it. We have to know they're mutually exclusive somehow. So let's look at a couple of other examples. Let's take a look at a deck of cards. So here's your standard deck of cards. Make that a little bit bigger. If you're not familiar with it, there's ace through 10. So that's like 1 through 10. And then we have jack, queen, king. And so that's 10, 11, 12, 13 of each suit. Suits are spades, clubs, hearts, spades, and diamonds. We have two different colors also. Variety of combinations we can throw out. Suppose I wanted to find the probability of drawing a heart or drawing a club. And so whenever I get an or, I ask, oh, do these guys have anything in common? Are they mutually exclusive? Can you be a heart and a club at the same time? The answer is no, you can't. So that means since these guys are mutually exclusive events, heart versus club, mutually exclusive, then that means this must be the probability of getting a heart plus the probability of getting a club. Which, let's see, hearts. How many hearts are there? There are 13 hearts out of 52 cards. You might also say it's 1 out of 4 if you wanted to reduce it. 13 clubs out of 52, which adds together to give me 26 out of 52, which you could reduce to 1/2 if you wish, or say it's 50% or 0.5, lots of options. All right, let's repeat that. How about the probability of getting a heart or a face card? Face cards are the ones with faces on them, the jack, the queen, and the king. So I can directly add their separate probabilities if I know they have nothing in common. So is it possible to be a face card and a heart at the same time? And the answer is yeah, we've got this one, and this one. So they do have something in common. So they're not mutually exclusive. So that means their probabilities, this probability of an or is going to be the probability of getting a heart plus the probability of getting a face, let's call that F, minus the probability of their intersection because I double counted those 3 cards. So heart and face. So hearts, there are 13 of them. Face cards, there are 3 times 4 or 12 of them. But I just counted these 3 cards twice. I counted them in the heart section and I counted them in the face card section. So then I have to subtract the intersection, which are the 3 face hearts. And so then I have to subtract 3 out of 52. So that's what, 25 minus 3 is 22 out of 52 is that probability, which you could reduce if you like. I'm going to leave it like that. So that's the idea of mutually exclusive, and mutually exclusive makes addition easier. Mutually exclusive means the two things we're looking at don't have anything in common. I'm going to do a recording next of independence. See you soon.